Tonight, imagine shrinking your sense of scale far beyond anything your intuition is comfortable with. Not just smaller than cities, or mountains, or grains of sand, but smaller than atoms. Smaller than the particles that make atoms possible, smaller than anything you have ever been told can meaningfully exist. Imagine following reality itself as it narrows, layer by layer, until it reaches a boundary where the very ideas of distance, space, and time begin to unravel. There is a point at which the universe seems to say, no further. A limit beyond which our best descriptions stop working, not because we lack imagination, but because nature itself refuses to cooperate. This boundary is known as the Planck length, and understanding it quietly changes how you see everything. Most people have never heard of it. It does not appear in daily life. You will never measure it with a ruler, a laser, or the most advanced instrument humanity has ever built. And yet, it may be the most fundamental distance in all of physics. It marks the frontier where our two greatest achievements, quantum mechanics and general relativity, collide, contradict each other, and fall silent. To appreciate why this length matters, we need to begin where human understanding always begins, with scale we can feel. You are roughly human-sized. Somewhere between 5 and 6 feet tall. At this scale, the world feels solid, continuous, reliable. Objects have definite shapes. Space feels smooth. Time flows evenly. You move through a world that seems intuitively understandable, governed by rules that feel consistent and familiar. Your eyes, remarkable as they are, have limits. The smallest object you can resolve without help is about the width of a human hair, roughly 1/10 of a millimeter. Anything smaller begins to blur into invisibility. For most of human history, this boundary defined the edge of reality. What lay beneath it was speculation, philosophy, or myth. Then, in the late 17th century, something profound happened. Anton van Leeuwenhoek, working with handcrafted microscopes, peered into drops of pond water and discovered an entire universe no one had ever suspected existed. Tiny organisms swam, twisted, multiplied, living things at scales 1,000 times smaller than anything the naked eye could see. He examined scrapings from his own teeth and found creatures living there as well, unseen companions inhabiting every human mouth. Reality, it turned out, was layered. The microscope did more than reveal small things. It revealed a pattern. Every time humans learned to look closer, the universe responded by becoming more complex, not less. Beneath visible life were cells. Inside cells were structures. Inside those structures were molecules. Each discovery suggested that what we perceive is only a surface, not a foundation. As lenses improved through the 18th and 19th centuries, scientists traced this chain deeper. But eventually, light itself became the obstacle. Visible light has a wavelength, and anything smaller than that wavelength cannot be resolved, no matter how perfect your lenses are. This imposed a natural limit on optical microscopes. Once again, physics answered with a new tool. In the 20th century, electron microscopes replaced light with electrons, particles that also behave like waves, but with wavelengths thousands of times shorter. This allowed scientists to see viruses, large molecules, and structures at the nanometer scale. The world of chemistry came into view. Bonds, reactions, and molecular machinery revealed themselves not as abstractions, but as tangible architecture. And beneath chemistry lay atoms. Atoms are astonishingly small. A typical atom measures about 1/10,000,000th of a meter across. Line up 10 billion of them, and you would span the length of a single meter. For centuries, atoms were nothing more than an idea. In ancient Greece, Democritus proposed that matter must be made of indivisible units, which he called atomos, uncuttable. Aristotle rejected the notion, insisting matter was continuous, infinitely divisible. For nearly 2,000 years, Aristotle's view prevailed. What changed was evidence. In the 19th century, chemists noticed something strange. Elements always combined in fixed ratios. Water was always 8 parts oxygen to 1 part hydrogen by mass. Carbon dioxide always followed the same proportions. This made sense if matter was made of discrete building blocks with specific masses. Atoms explained patterns that continuity could not. Still, no one had seen one. That changed in the early 20th century. Albert Einstein, studying the jittery motion of tiny particles suspended in fluid, showed that their random movement, Brownian motion, could only be explained if invisible atoms were constantly colliding with them. For the first time, atoms were no longer philosophical conveniences. They were measurable, calculable, real. But atoms themselves were not the end. In 1897, J. Thomson discovered the electron, revealing that atoms had internal structure. A little later, Ernest Rutherford fired high-energy particles at thin sheets of gold and found that while most passed through, a few bounced back violently, as if striking something impossibly dense. Atoms, he realized, were mostly empty space, with nearly all their mass concentrated in a tiny central nucleus. If an atom were the size of a football stadium, its nucleus would be no larger than a grain of sand at the center. Inside that nucleus were protons and neutrons. For a time, these seemed fundamental. But particle accelerators soon shattered that assumption as well. Protons and neutrons turned out to be made of even smaller entities called quarks, bound together by gluons, carriers of the strong nuclear force. By the mid-20th century, humanity had peeled reality down to scales smaller than anyone in antiquity could have imagined. And at each step, something strange happened, the closer we looked. The less the universe resembled the solid world we know. At the quantum scale, particles stopped behaving like tiny billiard balls. They became probability clouds, existing in superpositions, lacking definite positions or velocities until measured. Size itself became a slippery concept. Quarks and electrons, as far as experiments can tell, appear to have no size at all. They behave as point-like objects with no internal structure. And yet, physics tells us there must be a limit. This limit does not come from engineering. It does not arise because our machines are insufficient. It is woven into the fabric of the laws themselves. The closer we try to probe reality, the more violently reality responds. To see smaller distances, we must use higher energies. Shorter wavelengths mean more energetic probes. But energy has consequences. Concentrate enough energy into a small region, and according to Einstein's theory of gravity, spacetime itself begins to curve. Push this far enough, and you create a black hole, a region from which nothing, not even light, can escape. There exists a scale where the energy required to probe a distance would collapse that distance into a black hole, hiding it forever. That scale is the Planck length. At approximately 1.6 times 10 to the minus 35 meters, it is staggeringly small. To put this into perspective, if you enlarge the Planck length to the size of a grain of sand, a proton would be larger than the observable universe. The gap between everyday reality and this scale is not just large, it is beyond normal comprehension. And yet, this length emerges naturally when you combine three fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant. These numbers govern relativity, gravity, and quantum mechanics, the three pillars of modern physics. When combined in the only way that produces a length, they yield this value, as if nature itself insists upon it. Below this scale, space may no longer behave like space. Time may no longer behave like time. The smooth fabric described by Einstein may dissolve into something grainy, turbulent, or entirely unfamiliar. The Planck length is not just a small measurement. It is a warning sign. A boundary marker. A quiet statement from the universe that our deepest theories, successful as they are, do not tell the whole story. And beyond that boundary lies a question humanity has not yet answered: what is reality made of, when space itself can no longer be divided? That is the journey we are beginning. As we move closer to this boundary, something subtle but profound begins to happen. The problem is no longer just that things are small. The problem is that our ordinary ideas about what it means for something to exist start to lose their meaning. At the heart of this lies one of the most unsettling discoveries in all of science. The universe does not allow perfect knowledge. In the classical world, the world of everyday experience, this idea feels almost offensive. If you know where something is and how fast it's moving, you can predict where it will be later. That assumption underlies everything from throwing a ball to calculating planetary orbits. For centuries, physics rested on the belief that the universe is ultimately predictable, if only we gather enough information. Quantum mechanics shattered that belief. In 1927, Werner Heisenberg showed that there is a fundamental limit to how much you can know about certain pairs of properties at the same time. The most famous of these pairs is position and momentum. The more precisely you measure where a particle is, the less precisely you can know how fast it is moving, and in which direction. This is not a flaw in your instruments. It is not a limitation of human ingenuity. It is a feature of reality itself. Particles do not possess perfectly defined positions and momenta simultaneously. Nature does not store that information in the way classical physics assumed. This matters deeply when we try to probe small distances. To locate a particle very precisely, you need to use a probe with a very short wavelength. Short wavelengths require high energy. But high energy disturbs the particle's motion, injecting uncertainty into its momentum. There is no clever workaround. The trade-off is built into the structure of the universe. At human scales, this effect is negligible. At atomic scales, it becomes noticeable. At subatomic scales, it dominates everything. And when gravity enters the picture, the situation becomes even stranger. Einstein taught us that mass and energy are two sides of the same coin. Energy curves spacetime just as mass does. This means that as you concentrate more energy into a smaller region, precisely what you must do to probe tiny distances, you increase the curvature of spacetime itself. Push far enough, and the region collapses into a black hole. There is a point where the wavelength of your probe equals the size of the black hole it would create. Below that point, any attempt to measure a distance destroys the very information you are trying to uncover. Space hides itself behind an event horizon. This is not speculation. It is the unavoidable consequence of combining quantum mechanics with general relativity. The distance at which this happens is the Planck length. It marks the smallest scale at which the idea of distance retains any operational meaning. Below it, where it stops being a well-defined question. To understand why this length has such a special status, we need to examine where it comes from. Physics is governed by a small set of numbers that seem to be woven into the fabric of reality. Among these, three stand out as especially fundamental. The speed of light sets the ultimate limit on how fast information can travel. Planck's constant sets the scale at which quantum effects become unavoidable. The gravitational constant sets the strength of gravity itself. Individually, these numbers govern separate domains of physics. Together, they define a regime where all known theories must interact. By combining them through dimensional analysis, physicists discovered something remarkable. There is only one way to combine these constants to produce a quantity with units of length. The result is the Planck length. This is not an arbitrary choice. It is the only length scale that can be built from the constants that define our universe. From the same constants, we can also define a Planck time, the time it takes light to travel one Planck length. A Planck mass. A Planck energy. A Planck temperature. All of these values are extreme, far removed from everyday experience. The Planck temperature, for example, is about 10 to the 32 Kelvin. At such temperatures, the distinction between particles dissolves. Forces merge. Space and time themselves may lose their familiar roles. This collection of values defines what physicists call the Planck scale, the regime, where quantum gravity becomes unavoidable. And here we encounter a deep problem. Quantum mechanics is spectacularly successful at describing the small. General relativity is equally successful at describing gravity and the structure of spacetime on large scales. Both theories have been tested to extraordinary precision in their respective domains. But when you try to apply them together, they refuse to cooperate. Quantum mechanics treats spacetime as a fixed stage, a background on which particles and fields act. General relativity treats spacetime as a dynamic entity, shaped and curved by energy and matter. At the Planck scale, both perspectives must be true simultaneously, and they are incompatible. When physicists attempt to describe gravity using the methods of quantum field theory, the mathematics breaks down. Calculations produce infinities that cannot be removed. The tools that work perfectly for the electromagnetic force and the nuclear forces fail catastrophically for gravity. This failure is not a minor technical glitch. It is a signal that our description of reality is incomplete. At very small scales, quantum fields fluctuate wildly. Even in empty space, particles briefly appear and disappear, borrowing energy from the vacuum in accordance with the uncertainty principle. These fluctuations are real. They have been measured. They shift energy levels in atoms and produce subtle forces between closely spaced objects. But at the Planck scale, these fluctuations become so intense that they should dramatically distort spacetime itself. Space, instead of being smooth and continuous, may become turbulent, foaming with tiny black holes, wormholes, and violent geometric distortions that appear and vanish in unimaginably short times. Physicist John Wheeler famously described this as spacetime foam. At large scales, spacetime looks calm and orderly, like the surface of an ocean seen from an airplane. From far above, the water appears smooth and uniform. But descend closer, and waves emerge. Descend further, and turbulence appears. At the smallest scales, the surface is chaotic, churning, unpredictable. Spacetime, Wheeler suggested, behaves the same way. Smooth and geometric at large scales. Violent and uncertain at the smallest ones. In such a regime, familiar concepts break down. Distance is no longer stable. Geometry fluctuates. The idea of a fixed background dissolves. Space itself becomes a quantum object, subject to uncertainty just like particles. This is why physicists believe that the Planck length is not merely small, it is fundamental. It marks the scale at which spacetime itself must be described quantum mechanically. And once you accept that space and time may not be continuous, a radical possibility emerges: space itself may be made of discrete units. Just as matter is composed of atoms, space may be composed of indivisible building blocks, with the Planck length setting their size. Below that scale, there may be no in-between. No smaller distance to divide into. Geometry becomes granular. This idea is deeply unsettling. It challenges centuries of mathematical intuition built on continuous space and time. Calculus, the language of physics, assumes infinite divisibility. But nature may not share our mathematical preferences. If space is quantized, then time likely is as well. There would be a smallest unit of time, a fundamental tick of the cosmic clock. Between one tick and the next, nothing happens, not because nothing occurs, but because time itself does not exist there. At such scales, asking what happens between moments may be as meaningless as asking what lies between two adjacent pixels on a screen. The Planck length, then, is not just a measurement. It is a conceptual boundary. On one side lies the universe as we know it, smooth, geometric, describable. On the other side lies a realm where our current language fails. And yet, the universe does not stop there. Whatever reality is made of beneath the Planck scale, it still gives rise to everything we see: stars, galaxies, planets, life, and thought itself. Somewhere between this violent, foaming quantum geometry and the calm spacetime of everyday experience, order emerges. Understanding how that happens is one of the deepest questions in all of science. And it is the question that drives the search for a theory of quantum gravity. To search for a theory of quantum gravity is to accept, from the beginning, that something about our picture of reality must change. Not slightly. Not cosmetically. But fundamentally. Every successful theory in physics rests on assumptions about what exists and how it behaves. Newton assumed absolute space and absolute time. Einstein showed that space and time are flexible, woven together, shaped by energy. Quantum mechanics then revealed that certainty itself is an illusion, that probability lies at the heart of nature. Quantum gravity asks us to go one step further. It asks whether space and time themselves are emergent, whether they are not fundamental ingredients of reality, but consequences of something deeper. This is not a philosophical luxury. It is a mathematical necessity. When physicists attempt to calculate quantum processes involving gravity using the same methods that work for the other forces, the results explode into infinities. These are not small discrepancies. They are catastrophic failures. The equations stop making sense, producing meaningless results no matter how carefully they are handled. In quantum field theory, infinities are not unusual. They appear regularly, but physicists have developed techniques called renormalization to tame them. These techniques work astonishingly well for electromagnetism and the nuclear forces. They allow us to make predictions that match experiments to many decimal places. Gravity refuses to cooperate. No matter how the calculations are arranged, gravity stubbornly produces infinities that cannot be absorbed or cancelled. This tells us something crucial. General relativity, as powerful as it is, cannot be the final word on gravity. It is an effective theory, a remarkably accurate approximation that works beautifully at large scales, but breaks down when pushed too far. At the Planck scale, a deeper description must take over. What might that description look like? Over the past several decades, physicists have explored multiple paths toward quantum gravity. Each begins from a different intuition about what needs to change. Each offers a radically different vision of what reality might be made of. One approach suggests that the problem lies in our assumption that particles are point-like. Points have no size, no extension. When interactions occur at a single point, infinities arise naturally. Perhaps, then, the universe avoids these infinities by ensuring that nothing is truly point-like. This idea leads to string theory. In string theory, the fundamental building blocks of nature are not particles but tiny, one-dimensional strings, vibrating at the Planck scale. These strings can oscillate in different patterns, and each pattern appears, at low energies, as a different particle. An electron is one vibration. A quark is another. A photon yet another. Just as a single violin string can produce many notes depending on how it vibrates, a single type of fundamental string can give rise to the entire zoo of particles we observe. The crucial feature is size. Strings are not infinitely small points. They have length, about a Planck length. This smears out interactions, replacing violent point-like collisions with gentler, extended processes. The infinities that plague quantum gravity calculations disappear. Remarkably, gravity emerges naturally in this framework. One of the vibration patterns of a string corresponds to a particle with exactly the properties expected of the graviton, the hypothetical quantum carrier of gravity. Gravity is not added by hand. It is built into the theory from the start. This was an unexpected gift. String theory was not originally designed to explain gravity. Yet gravity insisted on appearing, as if the mathematics itself demanded it. But string theory comes with a price. For the equations to be consistent, the universe must have more dimensions than the 3 of space and 1 of time we experience. Depending on the version, string theory requires 10 or 11 total dimensions. The extra dimensions are not large and visible. They are tightly curled up, compactified into intricate geometric shapes at each point in space. From far away, space appears three-dimensional, just as a garden hose looks like a line from a distance. But zoom in close enough, and new directions reveal themselves, wrapped into tiny loops. The shapes of these hidden dimensions matter. Their geometry determines which particles exist, their masses, and the strengths of the forces between them. In this view, the laws of physics are not arbitrary. They are consequences of geometry at the Planck scale. This idea is both breathtaking and unsettling. It suggests that the properties of our universe, everything from the mass of the electron to the stability of atoms, may be determined by the shape of dimensions we can never directly observe. It also implies that there may be many possible geometries, each corresponding to a different version of physics. Perhaps our universe is one possibility among many. Another approach to quantum gravity begins from a very different intuition. Instead of modifying particles, it questions the nature of space itself. This approach is known as loop quantum gravity. Rather than treating spacetime as a smooth continuum, loop quantum gravity proposes that space is fundamentally discrete. It is not made of points on a continuous grid, but of tiny, indivisible units woven together into a network. These units are not embedded in space. They are space. At the Planck scale, area and volume come in discrete chunks. There is a smallest possible area. A smallest possible volume. Geometry itself is quantized, much like energy levels in an atom. From a distance, this granular structure blurs into smoothness. Just as a solid object appears continuous even though it is made of atoms, spacetime appears continuous even though it may be composed of discrete elements. In this framework, gravity is not a force propagating through space. It is the behavior of the geometry itself as these quantum units rearrange and interact. Space evolves by changing its own connectivity. One of the most intriguing implications of this picture concerns singularities, those points of infinite density predicted by general relativity, such as the centers of black holes and the beginning of the universe. In classical physics, singularities signal breakdown. They are places where equations stop making sense. Loop quantum gravity suggests that these infinities are artifacts of assuming continuity where none exists. When space is quantized, collapse cannot proceed indefinitely. There is a smallest volume, a maximum density. Instead of an infinite singularity, matter reaches Planck scale density and then encounters a new effect, a quantum geometric pressure that resists further compression. In black holes, this could mean that the core is not a point of infinite density, but a region of extremely curved yet finite spacetime. In cosmology, it could mean that the Big Bang was not a beginning, but a bounce, a transition from a previous contracting phase into the expanding universe we observe today. This possibility radically reshapes our understanding of cosmic origins. Instead of asking, what came before the universe, we might ask what came before the bounce. Time may extend beyond the Big Bang, just as space extends beyond the horizon we can see. Other approaches exist as well. Some suggest gravity may become well-behaved at high energies through subtle effects that tame its growth. Others propose that spacetime emerges from networks of causal relationships or from deep principles of information theory. What all these ideas share is a recognition that the Planck scale is not just another frontier. It is the place where our assumptions about reality itself are put on trial. At that scale, the universe may no longer be a stage where things happen. It may be a process. A constantly fluctuating structure from which space, time, and matter all emerge together. We do not yet know which, if any, of these ideas is correct. We lack experiments powerful enough to probe the Planck scale directly. The energies required are far beyond anything we can produce. For now, theory must guide us where observation cannot. But even without definitive answers, the lesson of the Planck length is already clear. Reality is deeper than it looks. Smoothness may be an illusion. Continuity may be a convenience. And the universe we experience may be a calm surface floating atop a storm of quantum geometry far beneath. What we call space may be something the universe does, not something it is. If space is something the universe does, rather than something it simply is, then one of the most unsettling consequences follows naturally: what we perceive as fundamental may actually be secondary. Solid. Stable. Reliable, yet not primary. This idea forces us to confront a possibility that feels almost backwards. Perhaps the smallest scales are not the foundation from which larger structures are built. Perhaps instead, space and time themselves emerge from relationships, patterns, or information that are not spatial at all. To see why physicists take this idea seriously, we need to return to a problem that has quietly haunted modern science for decades: black holes. Black holes are not just exotic astrophysical objects. They are stress tests for our understanding of reality. They push gravity, quantum mechanics, and information to their breaking points simultaneously. According to general relativity, a black hole forms when matter collapses beyond a critical density. Once the event horizon forms, nothing inside can influence the outside universe. Not light. Not particles. Not signals of any kind. From the outside, the black hole appears defined by only a few properties: its mass, its charge, and its spin. Everything else about what fell in seems to vanish. But quantum mechanics forbids this. In quantum theory, information is never destroyed. It may be scrambled, hidden, transformed, but it cannot simply disappear. This principle underlies the predictability of quantum evolution and the consistency of the theory itself. When physicists realized that black holes appeared to destroy information, they encountered a paradox that cut to the core of both theories. Either general relativity was incomplete, quantum mechanics was wrong, or our understanding of both was deeply flawed. This conflict is known as the black hole information paradox, and it has driven much of the modern thinking about the Planck scale. Stephen Hawking famously showed that black holes are not completely black. Quantum effects near the event horizon cause them to emit radiation, now known as Hawking radiation. Over immense spans of time, black holes evaporate, shrinking until they eventually disappear. The troubling implication was this: if a black hole evaporates completely, and if all that remains is thermal radiation, then the detailed information about everything that fell into the black hole seems to be gone forever. That outcome is unacceptable in quantum mechanics. Resolving this paradox required physicists to rethink what space, time, and locality actually mean. One proposed resolution suggests that information is somehow encoded on the event horizon itself. Rather than being lost in the interior, it is stored on the boundary, spread thinly across the surface area of the black hole. As the black hole evaporates, this information slowly leaks back out, encoded in subtle correlations within the radiation. This idea led to a profound realization: the maximum amount of information that can be stored in a region of space does Not scale with its volume, but with its surface area. This was shocking. In everyday experience, storage capacity scales with volume. A larger box holds more objects. A larger hard drive holds more data. But black holes suggested something radically different. The universe behaves as if information is fundamentally two-dimensional. This insight became known as the holographic principle. Just as a two-dimensional hologram can encode a three-dimensional image, the information describing a region of space may be fully contained on its boundary. The interior, in some sense, emerges from the boundary description. If this principle is correct, then space itself is not fundamental. It is a derived concept, arising from more basic degrees of freedom that live on lower dimensional surfaces. The Planck length plays a central role here. It sets the smallest meaningful unit of area, a Planck area, on which information can be stored. Each such area can encode, at most, a finite amount of information. Space, then, becomes a kind of information storage system, with resolution limited by the Planck scale. From this perspective, spacetime is not infinitely detailed. It has a maximum information density. Beyond that, the notion of more detail simply does not exist. This reframes the Planck length not as a barrier imposed by technology or energy, but as a fundamental pixel size of reality. And once reality has pixels, continuity becomes an illusion. But the holographic principle goes further. In certain theoretical models, entire universes with gravity can be exactly described by quantum theories without gravity living on their boundaries. In these models, spacetime geometry emerges from patterns of quantum entanglement. Entanglement is one of the strangest features of quantum mechanics. When particles are entangled, their properties are correlated in ways that cannot be explained by classical signals. Measure one, and the state of the other is instantly affected, no matter how far apart they are. For years, entanglement was treated as a curiosity. Today, it is increasingly seen as central. Some physicists now believe that the fabric of spacetime itself is woven from entanglement. Regions of space are connected because the underlying quantum degrees of freedom are entangled. Change the entanglement pattern, and you change the geometry of space. In this view, distance is not fundamental. It is a measure of how strongly different parts of the system are entangled. Close regions are strongly entangled. Distant regions are weakly entangled. If entanglement disappears, space tears apart. At the Planck scale, where quantum fluctuations dominate, these entanglement patterns may fluctuate violently. Geometry becomes unstable. Space loses its smoothness because the relationships that define it are in constant flux. This idea offers a new way to think about why the Planck length exists at all. It may mark the scale at which the notion of adjacency, the idea that two points are next to each other, ceases to have a stable meaning. Below that scale, the network of relationships that gives rise to space may no longer support a coherent geometric description. This also changes how we think about time. In many approaches to quantum gravity, time does not play the role we are used to. Instead of being a universal parameter that flows uniformly, time emerges from change, from correlations, from the evolution of relationships between quantum states. At the Planck scale, where fluctuations dominate, time may fragment into something discontinuous or relational. There may be no single cosmic clock, only local sequences of change. The familiar flow of time, past to future, moment to moment, may be an emergent phenomenon, arising only when the universe is viewed at scales far larger than the Planck length. This would mean that asking what happened before the Planck time may be as meaningless as asking what lies north of the North Pole. The Planck length, then, is not simply about smallness. It is about the limits of description. It marks the scale where space, time, causality, and information all intertwine so tightly that they can no longer be treated as separate concepts. And yet, from this murky, abstract realm, everything we know emerges. Galaxies form. Stars ignite. Planets coalesce. Life arises. Conscious beings look out into the universe and ask where it all came from. Somehow, the violent uncertainty of the Planck scale gives rise to order, structure, and meaning. Understanding how that happens may require us to abandon the idea that reality is built from things located in space and time. Instead, space and time themselves may be built from something deeper, something closer to logic, information, or relationships than to objects. The Planck length stands as a reminder that the universe is under no obligation to match our intuition. It only has to be consistent with itself. As strange as these ideas sound, they point toward a single, quiet conclusion: the universe is not constructed the way our senses suggest. What feels solid and continuous may be the end result of processes that are anything but. To understand how something as stable as space can emerge from something so unstable, it helps to think about a familiar illusion. When you watch a movie, you perceive smooth motion. Characters walk, cars drive, time flows naturally from one moment to the next. But underneath that seamless experience is a rapid sequence of still frames. The motion is not truly continuous. It emerges from discrete updates shown fast enough for your brain to blend them together. Physics may work the same way. At scales far larger than the Planck length, space-time updates so rapidly, and in such fine increments, that it appears smooth. Geometry flows. Time passes evenly. Distance feels continuous. But beneath that calm surface may lie a discrete, ticking process, updates occurring at the Planck scale, stitching reality together moment by moment. If this is true, then the Planck length is not simply the smallest possible distance. It is the resolution at which spacetime refreshes itself. This idea helps explain something that has puzzled physicists for generations: why the laws of physics look the same everywhere. No matter where we look in the universe, the same constants appear. The same particle masses. The same forces. The same mathematical relationships. From distant galaxies to the space between atoms, the rules do not change. If spacetime emerges from a deeper, universal structure, then this uniformity makes sense. The same underlying process runs everywhere, like the same code executing across a vast computational system. Some physicists have taken this analogy seriously, asking whether the universe, at its deepest level, behaves like a computation. In this view, the fundamental entities are not particles or fields, but bits of information. The evolution of the universe is the evolution of information, processed according to simple, universal rules. Space and time are bookkeeping tools, ways of organizing how information relates to itself. The Planck length then becomes a natural unit of information density. It sets how much information can be packed into a region before the system saturates. Beyond that, additional detail cannot be encoded, just as a digital image cannot display features smaller than a pixel. This perspective sheds new light on why attempts to probe smaller distances fail. It is not merely that our instruments are insufficient. It is that reality has no additional detail to reveal. Trying to see below the Planck length may be like zooming in on a digital photograph beyond its native resolution. You do not uncover finer structure. You simply magnify the same pixels. If this is correct, then many of our deepest questions must be rephrased. Instead of asking what space is made of, we may need to ask how information organizes itself into something that behaves like space. Instead of asking what time flows through, we may need to ask how sequences of change arise from underlying rules. Even the notion of causality, one event leading to another, may be emergent rather than fundamental. At everyday scales, causality feels absolute. Causes precede effects. Signals propagate forward in time. But at the Planck scale, where time itself may not be well defined, causality could be a large-scale approximation, arising only when fluctuations average out. This possibility has profound implications for cosmology. Consider the early universe. According to standard cosmology, the universe began in an extremely hot, dense state and has been expanding ever since. As we extrapolate backward in time, densities and temperatures increase, eventually reaching the Planck scale. At that point, our equations fail. But if time itself emerges from more primitive processes, then the question, what happened at the beginning of time, may be fundamentally misguided. There may not have been a first moment in the way we imagine. Instead, there may have been a transition from a non-temporal regime to a temporal one. Time, like space, may have crystallized. In such a picture, the Big Bang is not the birth of everything from nothing. It is the point at which the universe cooled enough for spacetime to become stable, for geometry to settle into a form that supports cause and effect, memory, and history. Before that, change may have existed without time. Structure without distance. Logic without location. This idea also reshapes how we think about the ultimate fate of the universe. If spacetime is emergent, then it is not guaranteed to exist forever. Under extreme conditions, inside black holes, at cosmic endpoints, or in regions of extreme curvature, the fabric of space and time may dissolve back into its underlying constituents. The universe may have phases, just as matter does. Solid spacetime at low energies. Quantum spacetime at high energies. Perhaps other phases we have not yet imagined. The Planck length marks the boundary between these phases. It is the line between geometry and pre-geometry. Between smoothness and structureless potential. Between the universe we inhabit and the deeper system that gives rise to it. And yet, despite its importance, the Planck length remains frustratingly inaccessible. We cannot build microscopes powerful enough to see it. We cannot collide particles at energies high enough to probe it directly. We infer its existence not through observation, but through consistency, through the demand that our theories not contradict themselves. This is both humbling and revealing. It tells us that human knowledge has limits, not because reality is unknowable, but because understanding requires new ways of thinking. Mathematics that does not assume continuity. Concepts that do not rely on space and time as primitives. Intuitions that accept emergence as fundamental. Every major advance in physics has required such a shift. Newton abandoned the idea that motion requires continuous pushing. Einstein abandoned the idea of absolute time. Quantum mechanics abandoned the idea of certainty. Quantum gravity may require us to abandon the idea that space and time are the stage on which reality unfolds. They may be the story the universe tells itself when viewed from far enough away. The Planck length is the punctuation mark at the end of that story, a reminder that beneath every smooth narrative lies a deeper grammar, hidden from direct view, yet responsible for everything we see. And as we approach the end of our journey, one question remains: if space and time are emergent, then what, ultimately, is real? That question does not yet have an answer. But asking it has already changed how we understand the universe. If we accept that space and time may not be fundamental, then the question of what is fundamental becomes unavoidable. Physics, at its deepest level, is no longer asking what things are made of, but what must exist in order for experience itself to be possible. This marks a profound shift. For most of scientific history, progress meant finding smaller pieces. Stones became minerals. Minerals became molecules. Molecules became atoms. Atoms became particles. Each step felt like moving closer to bedrock. But at the Planck scale, the ground gives way. There may be no smallest thing, only smallest relationships. In many modern approaches, the fundamental ingredients of reality are not objects with positions, but abstract Elements connected by rules. Networks. Graphs. Interactions. Information flowing from one state to another. Space appears only when these connections arrange themselves in stable, large scale. Patterns. In such a universe, location is not primary. Adjacency is. Two regions are close not because they are near in space, but because they are strongly connected in the underlying structure. Distance becomes a derived concept, meaningful only when the network is coarse-grained into something that resembles geometry. This idea helps explain why the Planck length appears as a hard limit. Below that scale, the network does not support finer notions of separation. There is no meaningful way to say that one element is half a Planck length away from another, because distance itself has not yet emerged. The universe, at that level, may not be spatial at all. This perspective also reshapes how we think about measurement. In everyday physics, measurement reveals properties that already exist. You measure a ruler, and its length is simply read off. But in quantum mechanics, measurement plays a more active role. It does not merely reveal reality, it helps define it. At the Planck scale, this may be taken to an extreme. Without a stable spacetime backdrop, there may be no definite properties until interactions occur. Reality becomes relational. Things exist only in relation to other things. This is deeply counterintuitive, but it aligns with a growing realization in physics that isolation is an illusion. Nothing exists completely on its own. Every system is part of a larger web of interactions. From this viewpoint, the Planck length is not where reality ends. It is where our habit of thinking in terms of isolated objects fails. Consider again the question of size. We are accustomed to imagining smaller and smaller distances as simply more zoom. But zoom assumes that what you are looking at already exists in a spatial sense. If space itself emerges only above a certain scale, then zooming past that scale is meaningless. There is nothing to zoom into. This reframes a classic philosophical question. Is the universe infinitely divisible? For centuries, mathematicians and philosophers assumed the answer was yes. Between any 2 points, there is another point. And another. And another. But physics may be telling us that this assumption, while mathematically convenient, is physically false. The universe may be finitely divisible, not because it is coarse in a crude way, but because its deepest structure does not support infinite subdivision. The Planck length represents that threshold. This has subtle but far-reaching consequences. For example, it suggests that the infinities that plague physics, singularities, infinite densities, infinite energies, are not real features of nature, but artifacts of applying continuous mathematics beyond its domain of validity. When equations predict infinity, they may be signaling not a physical truth, but a conceptual mistake. This insight echoes a pattern seen throughout the history of science. Whenever infinities appear in physical predictions, they usually indicate that a theory has been pushed beyond where it applies. The ultraviolet catastrophe in classical physics led to quantum theory. The infinite self-energy of the electron led to renormalization. Singularities in gravity may be pointing us toward quantum spacetime. In this sense, the Planck length is not a wall, but a signpost. It tells us where old tools must be replaced with new ones. Yet even as we talk about emergence and information, it is important to remember something grounding. Whatever the universe is doing at the Planck scale, it is doing it consistently. The same underlying rules give rise to the same macroscopic laws everywhere we look. Stars shine the same way in distant galaxies as they do nearby. Atoms behave identically across the observable universe. This regularity is not trivial. It suggests that the deep structure beneath spacetime is not chaotic in an arbitrary sense, but governed by simple, universal principles. Simplicity, not complexity, may lie at the foundation. This idea has appeared before. Newton's laws were simple. Maxwell's equations were elegant. Einstein's field equations, though mathematically demanding, were conceptually unified. Each time physics has gone deeper, it has discovered fewer assumptions, not more. The Planck scale may follow the same pattern. What appears as wild complexity, foaming spacetime, fluctuating geometry, quantum uncertainty, may emerge from underlying rules that are astonishingly simple. The difficulty lies not in the rules themselves, but in translating them into the language of space and time that we instinctively use. This also hints at why the Planck length feels so alien. Our brains evolved to navigate a world many orders of magnitude larger. We are tuned to patterns that persist over long times and large distances. The microstructure of reality is not something we were built to intuit. And yet, through mathematics and careful reasoning, we can glimpse it. We can infer that space has a smallest meaningful unit. That time may tick rather than flow. That geometry may be quantized. That information may be more fundamental than matter. None of these ideas diminish the reality of our experience. On the contrary, they enrich it. They tell us that the smooth world we inhabit is not an illusion, it is an achievement. It is what reality looks like when viewed from far enough away for its deepest instabilities to cancel out. The universe is not fragile. It is robust. And the Planck length is evidence of that robustness. It is the scale at which the universe protects itself from paradox, from infinite regress, from meaningless questions. It is where reality draws a line and says, this is as far as description goes. Beyond that, not because nothing exists, but because existence itself takes on a form we have not yet learned how to describe. And perhaps, in time, we will. As we approach the deepest implications of the Planck length, something unexpected happens. The conversation stops being only about physics and starts brushing against questions that humans have asked long before equations existed. Questions about limits. About meaning. About whether reality has an ultimate foundation, or whether every explanation simply gives way to another layer beneath it. For most of history, the idea that the universe might have a smallest scale would have felt unnatural. Ancient thinkers were divided on this. Some argued that matter must be divisible forever, that continuity was essential to reality. Others believed that endless division made no sense, that at some point, there must be an indivisible unit. What modern physics has done is transform that philosophical debate into a quantitative one. The Planck length is not chosen because it feels philosophically satisfying. It emerges because our best theories demand it. When quantum uncertainty and gravity are both taken seriously, infinite divisibility stops being possible. Nature pushes back. And that pushback may be telling us something profound about how reality avoids contradiction. Imagine a universe with no minimum length. In such a universe, you could localize energy into an arbitrarily small region. But energy gravitates. As the region shrinks, gravity grows stronger. Without a lower bound, nothing would prevent runaway collapse at every scale. Spacetime would be unstable. The universe would tear itself apart into singularities. The existence of a minimum length may be what makes a stable universe possible at all. In that sense, the Planck length is not a limitation. It is a safeguard. It ensures that the laws of physics remain self-consistent. It prevents infinite feedback loops. It sets a boundary that protects reality from mathematical self-destruction. This perspective changes how we think about fundamental limits. Instead of seeing them as barriers to knowledge, we can see them as features that make existence coherent. The speed of light is a limit, but it makes causality possible. Absolute zero. Temperature is a limit, but it gives meaning to thermal motion. The Planck length may be another such limit, a constraint that allows spacetime itself to function. And yet, this raises a subtle Question. If the Planck length is fundamental, is it the same everywhere and everywhen? All evidence suggests that it is. The constants that define it appear to be universal. They do not vary across space or time, at least within the precision of our measurements. This universality hints at something deeper. The Planck scale may be woven into the very logic of the universe, not just its material content. If so, then every region of space, every galaxy, every atom, every void, rests upon the same microscopic rules. The universe is not stitched together from different fabrics. It is one fabric, patterned differently at different scales. This brings us to a quiet but radical idea. Perhaps the Planck scale is not something we will ever see directly, even in principle. In science, progress often comes from building better instruments, bigger telescopes, faster accelerators, more sensitive detectors. But some limits are not technological. They are conceptual. If probing below the Planck length necessarily destroys the information you're trying to measure, by collapsing spacetime into a black hole, or by exceeding the universe's information capacity, then no future technology, no matter how advanced, can bypass that restriction. This does not mean that the Planck scale is unknowable. It means it must be understood indirectly. Just as we infer the existence of atoms long before we could image them, we may infer the structure beneath spacetime through its consequences at larger scales. Subtle deviations, statistical patterns, constraints on what is possible. In fact, physicists are already searching for such clues. They look for tiny violations of symmetry, minuscule delays in the arrival times of photons from distant cosmic explosions, quantum noise imprinted on the cosmic microwave background. Any hint that spacetime is not perfectly smooth, but has an underlying grain. So far, spacetime has proven remarkably well behaved. If there is a microstructure, it hides itself extremely well. This itself is a clue. It suggests that whatever exists at the Planck scale does not simply sit beneath spacetime like bricks beneath a floor. It may be more subtle, more relational, more abstract than any ordinary structure. Which brings us back to emergence. Emergence is the idea that complex behavior can arise from simple rules without being explicitly encoded in them. Temperature emerges from the motion of molecules. Pressure emerges from countless collisions. Consciousness emerges from neural activity, even though no single neuron is conscious on its own. In each case, the emergent phenomenon is real. Temperature is not an illusion. Consciousness is not a trick. But neither exists at the level of the fundamental components. Spacetime may be the same. If so, then asking what exists below the Planck length may be like asking what temperature exists inside a single molecule. The question is misframed. The concept simply does not apply. This reframing has an important psychological consequence. It softens the anxiety that often accompanies discussions of ultimate limits. Humans are deeply uncomfortable with boundaries. We want to know what lies beyond every horizon. When told that something is the smallest possible, the mind immediately asks what comes after that. But perhaps the need for after is itself a habit formed at larger scales. At the deepest level, reality may not be layered like an onion, with endless shells to peel away. It may be more like a network, where meaning arises from relationships rather than depth. In such a universe, the Planck length is not the bottom of a stack. It is the scale at which stacking stops making sense. This does not diminish the wonder of the universe. If anything, it amplifies it. The fact that a coherent, stable cosmos can emerge from something so abstract, that galaxies, chemistry, biology, and thought itself can arise from rules operating at a scale where space and time dissolve, is astonishing. It suggests that reality is not fragile. It is resilient. It can produce order from uncertainty, continuity from discreteness, meaning from mathematics. And perhaps that is the deepest lesson of the Planck length. It teaches us humility. Not by telling us that we can know nothing, but by showing us that knowledge has structure. That some questions must be asked differently. That understanding sometimes requires letting go of familiar categories. The universe does not end at the Planck length. Our language does. And beyond that, silence is not emptiness, but possibility, the possibility of new concepts, new mathematics, and new ways of understanding what it means for something to exist. We are not finished with that journey. We have only reached the edge of what our current ideas can say. Standing at that edge, it becomes clear that the Planck length is not merely a technical detail for physicists. It is a mirror held up to the limits of human understanding. Every time science has advanced, it has done so by discovering that the universe is stranger, subtler, and more layered than intuition suggests. The Planck scale is simply the latest reminder of that pattern, but it may also be the most profound. Because this time, the thing being questioned is not matter, or energy, or force. It is the stage itself. For centuries, space and time felt untouchable. They were the background assumptions behind every observation. Even when Einstein revealed that space-time could bend and stretch, it still existed as a geometric entity, something real. Something continuous. The Planck length challenges even that. It suggests that geometry is not sacred. That smoothness is not guaranteed. That what we call space may be a large-scale convenience. Not a fundamental truth. This realization quietly changes how we think about existence. If space and time are emergent, then the universe is not a collection of objects sitting somewhere. It is a web of relationships that, when viewed collectively, give rise to the appearance of location, duration, and motion. Existence becomes less about where something is, and more about how it relates to everything else. This has echoes far beyond physics. In philosophy, similar ideas have appeared again and again. That relations matter more than substances. That identity arises from interaction. That the whole cannot be reduced to its parts. Physics, often thought of as cold and reductionist, may be circling back to these ideas from a new direction, guided not by introspection, but by equations that refuse to work unless we let go of old assumptions. There is also a deeply human aspect to this story. The Planck length confronts us with the fact that there are questions we cannot answer by simply building bigger machines. At some point, understanding requires conceptual courage, the willingness to abandon comfortable mental models. This is not a weakness of science. It is its strength. Science does not promise certainty. It promises honesty. When a theory reaches its limits, it does not pretend otherwise. It signals, clearly and unambiguously, that something deeper awaits. The Planck scale is such a signal. It tells us that our current map of reality is incomplete. Not wrong, but partial. Like a map of Earth drawn before the discovery of continents beyond the horizon. And just as those earlier maps were still useful, still powerful, still capable of guiding exploration, so too are our current theories. Quantum mechanics and general relativity are not invalidated by the Planck length. They are contextualized. They describe how the universe behaves when spacetime is stable and smooth. They are the effective rules of a particular phase of reality. But beneath that phase lies something else. Something that does not look like space, or time, or matter, but nevertheless gives rise to all of them. It is tempting to ask whether we will ever fully understand that deeper layer. History offers a cautious optimism. There was a time when atoms were invisible and controversial. When the idea that matter was made of discrete units was ridiculed. There was a time when the curvature of space sounded absurd. when quantum uncertainty seemed like a failure rather than a feature. Each time, understanding required new mathematics, new experiments, and new ways of thinking. The Planck scale may demand the same. It may require theories that treat information as fundamental, or frameworks that describe reality without reference to space and time at all, or concepts that do not yet exist in our intellectual vocabulary. Whatever form the answer takes, it will not erase the mystery. It will deepen it. Because understanding does not eliminate wonder. It refines it. Knowing that space may be emergent does not make the night sky less beautiful. Knowing that time may not be fundamental does not make moments less meaningful. If anything, it makes them more precious. Every experience you have unfolds at scales unimaginably larger than the Planck length. Every thought, every memory, every sensation is part of a macroscopic world that emerges reliably from microscopic uncertainty. That reliability is extraordinary. It means that the universe, despite its deep quantum instability, produces a world where patterns persist long enough for stars to burn, planets to form, and life to evolve. The Planck length is part of that success story. It is one of the rules that keeps the universe from collapsing into chaos. One of the constraints that allows complexity to exist at all. And perhaps that is the most important thing to remember. The smallest length in the universe is not something we encounter directly. It does not shape our daily lives in any obvious way. But without it, or something like it, the universe might not support structure, history, or observers. In that sense, the Planck length is woven quietly into everything. Into the stability of atoms. Into the persistence of spacetime. Into the fact that there is a world at all. We may never see beyond it. We may never fully describe what lies beneath it. But we do not need to. Because understanding the existence of a limit already tells us something profound. Reality is not arbitrary. It is constrained, structured, and self-consistent in ways deeper than intuition alone could ever reveal. The Planck length is not the end of inquiry. It is the place where inquiry changes its character. Where questions about size give way to questions about meaning. Where the universe stops answering with pictures and starts answering with principles. And standing there, at that boundary, we are reminded of something essential: the universe is not obligated to be simple, intuitive, or fully accessible. Yet it is generous enough to be understandable at all. That may be its greatest mystery. When we step back and take in everything the Planck length implies, a quiet realization settles in: the universe is not built to satisfy human curiosity. And yet, remarkably, it is built in a way that allows curiosity to exist. That balance is delicate. On one hand, reality hides its deepest workings behind scales we cannot directly access. On the other, it leaves clues, consistent patterns, mathematical hints, boundaries that point toward deeper structure. The Planck length is one of those clues. It does not give us answers. But it tells us where answers must eventually come from. This is why the search for quantum gravity has continued for decades, even without experimental confirmation. Physicists are not chasing an aesthetic ideal. They are responding to a tension in the foundations of knowledge itself. Two theories that describe reality with extraordinary precision refuse to agree at the deepest level. That refusal demands resolution. And resolution, in science, has always come at a cost, the cost of abandoning assumptions that once felt obvious. Perhaps the hardest assumption to abandon is that reality must ultimately resemble something we can picture. Particles as tiny dots. Space as a grid. Time as a flowing line. At the Planck scale, picturing fails. What exists there may not be representable as an image at all. It may be describable only through abstract relationships, algebraic structures, or logical constraints. Reality, at its foundation, may be closer to mathematics. than to matter. This idea unsettles some and comforts others. For those who seek tangible substance beneath everything, it feels like a loss. For those who value coherence and consistency, it feels inevitable. Because mathematics has always been the language through which the universe speaks most clearly. The equations that define the Planck length do not reference any particular object or phenomenon. They arise from the constants that govern causality, uncertainty, and gravity. They reflect how information, energy, and geometry interact. In that sense, the Planck length is not about small things. It is about rules. It tells us that there is a limit to how finely the universe allows itself to be described. Not because of ignorance, but because description itself has structure. This perspective changes how we think about discovery. Instead of imagining a final layer where everything becomes simple and concrete, we may need to accept that the deepest layer is abstract. That understanding does not culminate in seeing smaller pieces, but in grasping more subtle principles. This also reframes the role of human thought. Our minds evolved to recognize patterns at the scales relevant to survival. We are good at tracking motion, estimating distances, predicting cause and effect in a world where spacetime is stable. We are not naturally equipped to reason about regimes where those concepts dissolve. And yet, through collective effort, mathematics, and imagination, we have managed to reach that edge anyway. That achievement is extraordinary. It means that even though we are embedded in the emergent layer of reality, we can infer the existence of what lies beneath it. We can detect the outline of the invisible through the way it constrains the visible. The Planck length is one such constraint. It shapes what is possible. It limits how energy can be localized. It governs the ultimate resolution of spacetime. It protects the universe from contradictions that would otherwise tear it apart. And it does all of this quietly, without fanfare, without revealing itself directly. There is a humility in that. The universe does not announce its deepest secrets. It allows them to be deduced, slowly, through patience and rigor. It rewards consistency over intuition, and coherence over comfort. In this way, the Planck length teaches a lesson not just about physics, but about understanding itself. Understanding is not about reducing everything to familiar terms. It is about learning which questions are meaningful at which scales. It is about recognizing when a concept has reached the end of its usefulness. Space, time, distance, duration, these are powerful ideas. They organize experience. They allow prediction. They make science possible. But they are not unlimited. At the Planck scale, they give way to something else. What that something else is remains an open question. It may be information. It may be relationships. It may be logic. It may be something entirely unforeseen. What matters is that whatever it is, it gives rise to a universe capable of reflection. A universe that can ask about its own limits. That fact alone is remarkable. From the smallest meaningful length arises a cosmos vast enough to contain stars, minds, and questions about existence. From rules operating far beyond perception emerges a world of color, sound, memory, and meaning. The Planck length reminds us that reality is layered, but not in a way that diminishes what we see. The surface is not fake. It is emergent. And emergence is not a flaw. It is a feature that allows complexity, stability, and life. So when we speak of the smallest length in the universe, we are not speaking of something remote or irrelevant. We are speaking of a principle that quietly underwrites everything we experience. The solidity of the ground beneath your feet. The persistence of moments in time. The continuity of cause and effect. All of it depends on limits you will never encounter directly. And perhaps that is the final insight the Planck length offers. Reality does not reveal itself by becoming smaller and smaller until it disappears. It reveals itself by setting boundaries that make structure possible. By saying, this far. And no further, not out of secrecy, but out of necessity. At that boundary, the universe is not closing a door. It is inviting us to rethink what it means to understand. At the end of this long descent into the smallest meaningful scale, we arrive somewhere unexpected. Not at a final object. Not at a final equation. But at a shift in perspective. The Planck length does not give us a picture of what lies beneath reality. It gives us a rule about how reality behaves. And that distinction matters. Throughout human history, we have assumed that understanding means uncovering what something is made of. Wood is made of fibers. Water is made of molecules. Matter is made of atoms. At each stage, progress meant peeling back another layer. But the Planck scale suggests that this metaphor eventually breaks. There may be no final layer of stuff waiting to be revealed. Instead, there may be a final layer of constraints, rules that determine what kinds of structures can exist at all. In this sense, the Planck length is less like a brick and more like a grammar rule. It does not tell you what sentences must be written. It tells you which sentences are possible. The universe, viewed this way, is not assembled from pieces. It is generated from principles. Some principles limit speed. Some limit certainty. Some limit density. And one of them limits divisibility. Together, these limits carve out a space of possibilities, a narrow corridor within which stable reality can exist. Stars, chemistry, biology, and thought are not guaranteed outcomes. They are solutions that fit within those constraints. This reframes the idea of fundamental. What is most fundamental may not be what is smallest, but what is most restrictive. The rules that leave the least room for variation. The ones that everything else must obey. The Planck length is one of those rules. It tells us that there is a finest resolution to the universe's fabric. Not because the universe is crude, but because it is precise. Precision requires boundaries. Without them, meaning dissolves into infinity. This also explains why the Planck length feels so resistant to intuition. Human intuition evolved in a world where boundaries are negotiable. You can cut a piece of wood in half. Then in half again. And again. Nothing in daily life prepares you for a boundary that is not practical, but principled. Yet physics is full of such boundaries. You cannot cool an object below absolute zero. You cannot transmit information faster than light. You cannot measure a particle's position and momentum with unlimited precision. These are not inconveniences. They are structural features of reality. The Planck length belongs in that same category. It is a statement about what questions the universe allows us to ask in spatial terms. Below that scale, questions about distance stop being well-defined, not because we lack imagination, but because the universe does not provide answers in that language. And that may be the most important takeaway of all. Understanding reality does not mean forcing it to conform to our preferred concepts. It means adapting our concepts to match reality. Space and time have served us extraordinarily well. They are the scaffolding of experience. They organize memory, prediction, and action. But they are not eternal truths. They are effective descriptions, valid, powerful, and real at the scales where we live. The Planck length marks the edge of their authority. Beyond it, something else takes over. Something that still gives rise to order, consistency, and law, but does so without relying on geometry as we know it. That realization does not make the universe colder or more alien. It makes it richer. It means that reality is capable of expressing itself in more ways than our senses alone could ever reveal. It means that the calm, continuous world we inhabit is a remarkable achievement of deeper processes, not a given. And it means that mystery is not a failure of knowledge, but a sign of depth. The Planck length does not end the story of physics. It opens a new chapter, one where the questions are not about smaller objects, but about more fundamental principles. About how structure emerges. About how information becomes geometry. About how change becomes time. We are still learning how to ask those questions properly. But even now, one thing is clear. The smallest meaningful length in the universe is not something we will ever touch, see, or measure directly. Yet it shapes everything we are. It shapes the stability of matter, the persistence of spacetime, the possibility of a universe complex enough to know itself. In that sense, the Planck length is not distant at all. It is present in every moment that unfolds smoothly. In every distance that feels continuous. In every cause that reliably leads to an effect. It is the quiet rule beneath the world, a rule that says reality is not infinitely fragile, not infinitely divisible, not infinitely arbitrary. It is constrained. It is structured. And because of that, it is knowable, at least in part. We may never cross the Planck boundary with instruments. But by recognizing that it exists, we have already crossed an intellectual one. We have learned that understanding does not always mean going further down. Sometimes, it means stepping back and seeing the limits themselves as the deepest form of explanation. And in that realization, the universe becomes not smaller, but profoundly, endlessly deep. And with that realization, the journey reaches a natural resting point, not because the mystery has been solved, but because it has been properly framed. The Planck length does not answer the ultimate question of what reality is. Instead, it tells us something just as important, how reality refuses to be questioned in certain ways. It defines the shape of our ignorance as much as the shape of our knowledge. This is a subtle but powerful insight. In everyday life, limits feel like failures. A wall blocks movement. A boundary denies access. But in physics, limits often reveal structure. They show where one description ends and another must begin. They tell us that the universe is not chaotic, but carefully constrained. The Planck length is one of those constraints. It tells us that space is not an infinitely stretchable canvas. That time is not an endlessly divisible flow. That the universe enforces coherence at its deepest level by refusing to allow meaningless questions to be asked. There is no distance smaller than the Planck length in the same way there is no temperature colder than absolute zero, not because nothing exists there, but because the concept itself ceases to apply. This realization changes how we think about exploration. Human curiosity often imagines progress as a straight line, farther, faster, smaller, deeper. But the Planck scale suggests that progress sometimes requires a turn rather than an advance. A shift in language. A change in what we consider fundamental. We may not reach deeper truth by probing smaller distances, but by discovering new ways to describe relationships, information, and emergence. And that is not a retreat from science. It is science doing what it has always done at its best, listening carefully to what nature allows, and adjusting its questions accordingly. The universe has spoken before in this way. When classical physics failed at small scales, quantum mechanics emerged. When Newtonian gravity failed at high speeds and strong fields, relativity emerged. Each time, reality did not become less understandable. It became understandable in a different way. The Planck length is another such message. It tells us that the universe is not obligated to provide a picture beneath every picture. That some layers of description are final not because they are simple, but because they are sufficient. Space and time, smooth and continuous, are not illusions. They are real features of the world we inhabit. But they are real in the same way that waves are real in the ocean, emergent, collective, and dependent on deeper dynamics. At the deepest level we can currently infer, the universe is not made of things arranged in space and time. Space and time themselves are arrangements, patterns that arise when deeper rules align in stable ways. This does not diminish the human experience. On the contrary, it gives it context. Every moment you experience unfolds at scales where spacetime is reliable, where cause leads to effect, where memory and anticipation make sense. That reliability is not trivial. It is earned by the universe through the enforcement of its deepest constraints. The Planck length is part of that enforcement. It is the reason the universe does not tear itself apart under its own laws. The reason infinities are kept at bay. The reason complexity can exist without collapsing into contradiction. In that sense, the smallest meaningful length is also a foundation, not of matter, but of possibility. And perhaps that is the most remarkable outcome of this entire story. From a scale so small it defies imagination emerges a universe vast enough to contain meaning. From limits on divisibility emerge histories, identities, and futures. From constraints arise freedom. The Planck length reminds us that reality is not a formless abyss beneath appearances. It is structured all the way down, structured in a way that allows appearance itself. We may never know exactly what exists beyond that boundary of description. But we know that whatever it is consistent enough to give rise to everything we see. Stars, galaxies, life, thought, and beings capable of wondering why there is a smallest length at all. That wonder is not incidental. It is part of the universe's expression at large scales, a reflection of deep order, surfacing as curiosity. So when we speak of the Planck length, we are not merely talking about an abstract number. We are talking about the quiet architecture that holds reality together. A boundary that is not an ending. A limit that is not a denial. A silence that is not empty. It is the place where the universe stops answering in images and starts answering in principles. And in learning to listen at that level, we do not lose the world we know. We understand it more deeply. There is something quietly profound about ending a journey not with an answer, but with a clearer sense of what answers can be. The Planck length teaches us that the universe is not infinitely permissive. It does not allow every imaginable structure, every conceivable question, every mathematical extension to correspond to something real. It selects. It constrains. It says yes to some possibilities and no to others. And from those constraints, everything else follows. This is easy to overlook, because human intuition is drawn to excess. We imagine infinite space, infinite time, infinite divisibility. Infinity feels powerful, elegant, complete. But nature, again and again, has shown a preference for finitude. Not smallness, but boundedness. Not simplicity, but restraint. Light has a maximum speed. Temperature has a minimum. Information has limits. And space itself appears to have a smallest meaningful scale. These limits do not impoverish reality. They enrich it. Without a maximum speed, causality would dissolve. Without quantum limits, atoms would be unstable. Without a minimum length, gravity and quantum mechanics would tear the universe into contradictions. Order depends on boundaries. The Planck length is one such boundary, and perhaps one of the most consequential. It marks the point where the universe stops tolerating certain kinds of questions, not out of secrecy, but out of coherence. It tells us that below a certain scale, the language of where and when no longer applies. And that is not a failure of understanding. It is understanding maturing. This is a difficult lesson for a species that equates knowledge with penetration, going deeper, cutting finer, seeing more. But some truths are not reached by going further down. They are reached by stepping sideways into new frameworks. The future of fundamental physics may not lie in probing smaller distances, but in uncovering deeper principles. Principles that explain why space, time, and matter appear at all. Principles that show how consistency, stability, and structure arise from something more abstract. That future may involve mathematics that does not assume continuity. Theories that do not begin with spacetime. Descriptions that treat information, relation, or symmetry as primary. It may require abandoning the idea that reality must be visualizable in any ordinary sense. And that is not unprecedented. No one has ever seen a wave function. No one has ever observed curved spacetime directly. These ideas live first in mathematics and only later in their consequences. Yet they are among the most successful descriptions of reality we have ever found. The Planck length belongs to that same category. It is not something you encounter. It is something you infer. And what it tells you is not how small things get, but how the universe stays sane. In a way, the Planck length is a kind of quiet kindness. It prevents the universe from collapsing under the weight of infinite possibilities. It ensures that questions remain meaningful. It allows reality to be structured enough to persist. And persistence is everything. Without it, there would be no long-lived stars. No stable chemistry. No memory. No evolution. No observers to ask questions at all. Every coherent moment you experience depends on the fact that spacetime behaves predictably at human scales. That predictability, in turn, depends on rules that operate far beneath perception, rules that include a smallest meaningful length. So while the Planck length feels remote, abstract, and irrelevant to daily life, it is anything but. It is part of the invisible scaffolding that makes daily life possible. It is present in the fact that the floor beneath you does not flicker in and out of existence. That distances remain distances. That time flows smoothly enough for thought to unfold. That causes reliably precede effects. These are not trivial features of reality. They are achievements. And they are achieved because the universe is constrained. Perhaps the deepest shift the Planck length invites is this: to stop thinking of limits as obstructions. And start seeing them as enablers. To recognize that what the universe refuses to allow is just as important as what it permits. In that light, the smallest length is not the end of curiosity. It is the refinement of it. It pushes us away from naive questions and toward better ones. Away from picturing reality as stacked layers of smaller objects, and toward understanding it as a hierarchy of descriptions, each valid within its domain. At large scales, geometry works. At small scales, probability dominates. At the smallest meaningful scales, even those concepts may give way to something more fundamental still. And that is not disappointing. It means the universe is deep, not just in size, but in structure. It means there is room for continued discovery. Not necessarily by going smaller, but by thinking differently. The Planck length stands as a reminder that the universe does not owe us intuitiveness. It owes us consistency. And consistency, it delivers. From that consistency emerges a world that can be explored, understood, and lived in. A world where limits do not suffocate wonder, but shape it. A world where the deepest truths are not always found at the smallest scales, but at the boundaries between what can be said and what must be reimagined. And perhaps that is where the real journey begins. And so, when all the equations are set aside and all the abstractions fall quiet, what remains is a simple but transformative insight: reality is not built without care. It is shaped, disciplined, and held together by limits that are as essential as the things they constrain. The Planck length is one of those limits. It does not announce itself in experience. You will never feel it under your fingers or see it through a lens. It leaves no obvious trace in the rhythm of daily life. And yet, it is present everywhere, quietly ensuring that the universe behaves in a way that allows experience to exist at all. It is easy to think of the smallest scales as remote, irrelevant to the human story. But the truth may be the opposite. The deepest rules of the universe are not distant curiosities. They are the reason the world feels stable enough to matter. Because stability is not guaranteed. A universe without constraints would not be a richer universe. It would be an incoherent one. Without limits on speed, cause and effect would unravel. Without limits on uncertainty, atoms would not hold together. Without a limit on divisibility, gravity and quantum mechanics would spiral into contradiction. The Planck length is part of the quiet architecture that prevents that collapse. It ensures that space does not fragment endlessly. That time does not dissolve into meaninglessness. That the universe retains enough structure to support memory, history, and identity. From that structure emerges everything we recognize as real. This reframes the relationship between the smallest and the largest scales. The vastness of the cosmos is not separate from the minuteness of the Planck length. They are connected. The same rules that govern the smallest meaningful distances also govern the formation of galaxies and the evolution of stars. The universe is not stitched together from unrelated parts. It is one continuous expression of the same underlying principles, manifesting differently at different scales. And those principles appear to be remarkably economical. Again and again, physics reveals that complexity does not require complicated foundations. It requires the right constraints. Simple rules, when applied consistently, can generate astonishing richness. The Planck length is one such rule. It does not tell the universe what to become. It tells it what it cannot be. And in doing so, it leaves room for everything else. This may be why the idea of a smallest length feels both unsettling and comforting. Unsettling, because it challenges the intuition that everything can be broken down forever. Comforting, because it suggests that reality is not infinitely fragile. There is a floor beneath which coherence does not fall apart. That floor is not a place. It is a principle. It marks the boundary where familiar concepts stop working, not because reality ends, but because our current language does. Beyond it, the universe continues, governed by rules we are only beginning to glimpse. What those rules are remains an open question. They may involve information, entanglement, symmetry, or ideas not yet imagined. They may require mathematics that has not yet been invented. They may force us to abandon assumptions we do not yet realize we are making. But whatever form they take, they must respect the constraint the Planck length represents. They must give rise to a world where space and time emerge reliably at larger scales. A world where cause and effect make sense. A world where complexity can persist long enough to be noticed. A world like ours. In that sense, the Planck length is not merely a scientific curiosity. It is part of the answer to a deeper question: why is there a universe that can be understood at all? The fact that reality enforces limits suggests that it is not arbitrary. That it is not a random explosion of possibilities. That it has an internal logic, a consistency that runs deeper than appearances. We are only beginning to learn how to listen to that logic. And perhaps that is the final lesson this journey offers. Understanding the universe is not about exhausting its mysteries. It is about learning where mystery belongs. It is about recognizing that some questions dissolve when asked at the wrong scale, while others come into focus only when we accept limits. The Planck length teaches us that the deepest truths may not lie beyond every boundary, but within the boundaries themselves. In the quiet discipline of what is allowed. In the structure imposed by what is forbidden. In the balance between possibility and constraint. From that balance emerges a universe capable of unfolding, remembering, and reflecting on its own Existence. A universe where a smallest meaningful length is not a barrier to wonder, but one of its sources. And in recognizing that, we do not reach the end of understanding. We reach a deeper respect for the way reality holds together, and for the remarkable fact that we are here, able to ask about it at all. As the journey draws to a close, what remains is not a solution, but a kind of clarity. A recognition that some questions are valuable not because they can be answered, but because they reshape how we see everything else. The Planck length does exactly that. It reframes the universe from something endlessly divisible into something delicately structured. It reminds us that reality is not held together by infinite freedom, but by carefully balanced constraints. That what we experience as smoothness, continuity, and stability is not the default state of existence, but an emergent achievement. There is a quiet beauty in this idea. It means the universe is not reckless with possibility. It does not allow anything to happen anywhere at any scale. It chooses. It restricts. It shapes. And through that shaping, it allows meaning to exist. Space exists because it does not exist in every possible form. Time flows because it does not fragment endlessly. Structure persists because divisibility has a limit. The Planck length is one of the places where that discipline becomes visible. It is the point where the universe stops offering geometry and starts offering principle. Where distance stops being a question with an answer, and starts being a question that no longer applies. Where our instinct to imagine smaller gives way to the need to imagine different. And this is not a loss. It is an invitation. An invitation to stop thinking of reality as a stack of objects and start thinking of it as a hierarchy of descriptions. To recognize that each layer of understanding has a domain where it works beautifully, and a boundary where it must give way to something deeper. At human scales, space and time are real, reliable, and indispensable. At atomic scales, probability and uncertainty take over. At the Planck scale, even those give way to constraints we are only beginning to understand. None of these layers cancel the others. They coexist. They support one another. They form a coherent whole. The smallest meaningful length in the universe does not make the universe smaller. It makes it more precise. It tells us that reality is not vague all the way down, but sharply defined where it needs to be. And perhaps that is why this idea resonates so deeply. Because it mirrors something about human understanding itself. We, too, operate within limits. We cannot know everything at once. We cannot see all scales simultaneously. We make sense of the world by using the right concepts at the right level, and letting go of them when they no longer apply. The universe appears to do the same. It does not offer infinite resolution. It offers sufficient resolution. Enough to build stars. Enough to support life. Enough to allow beings like us to wonder where it all comes from. The Planck length is part of that sufficiency. It is not a wall we crash into, but a line that quietly says, beyond this, meaning must be expressed differently. And in learning to accept that, we take a step closer to understanding not just the universe, but the nature of understanding itself. Because the deepest insight may not be about what exists at the smallest scale. It may be this: that reality is not obligated to be endlessly dissectable to be real. That depth does not require infinity. That limits can be the source of coherence, not its enemy. From that coherence emerges a universe vast enough to inspire awe, yet disciplined enough to endure. A universe that can be studied, questioned, and slowly understood, never completely, but always meaningfully. And standing within it, we are not outsiders looking in. We are part of the same structure. Subject to the same limits. Shaped by the same rules. The Planck length exists whether we know it or not. But knowing that it exists changes how we see everything else. It reminds us that the universe is not a careless accident, nor an infinite blur of possibility. It is a carefully balanced reality, deep, constrained, and quietly astonishing. And that may be more than enough.